Welcome. Okay, we'll go ahead and get started. Can the people on Zoom hear me okay and see the slide?
Yes.
Thank you. All right, today we're going to finish up chapter 16 and then we'll start on chapter 17. So more equilibrium stuff today. The other thing I wanted to mention is that next Thursday, March 25th, we'll have exam number 3. And that exam will cover chapter 15, 16, and 17. So, okay, so we've been talking about weak acids. And remember, weak acids were acids that dissociate partially. And so we're going to shift gears a little bit and talk about weak bases. Now, the stuff that we talk about with weak bases hopefully will sound very familiar because it'll be similar to what we were talking about with weak acids. With weak bases, these are bases that dissociate partially just as the weak acids do. So a lot of the things that we do to investigate weak bases and some of the calculations and things like that, some of the approaches to the calculations should look familiar or similar to the weak acids. So don't get too hung up on a weak acid versus weak base thing because a lot of it's going to be similar. Ammonia NH3 is probably the most famous is the right term, but at least that's a weak base that people use quite a bit and talk about a little bit. And so that'll be one that we talk about. And actually, you can see down at the bottom of this slide, we have that dissociation expression for ammonia. So ammonia plus water goes to ammonium ion and hydroxide ion. And if we write that equilibrium expression, we have NH4 plus times OH minus, so that's the products divided by the reactants, NH3 plus. Water, as usual in this type of equation, is a pure liquid, so it has a value of 1, so it doesn't show up in that equilibrium expression. Now, just as we had a K with a little a next to it and called that an acid dissociation constant, we have a similar constant for bases, a K with a small b subscript, and that's the base dissociation constant. So as I said, those equilibrium type calculations that we did for weak acids, we're going to use a similar approach for weak bases, except instead of solving and setting it equal to the acid dissociation constant, we'll set it equal to the base dissociation constant. The other thing I want to point out is that a lot of bases, especially for organic compounds, and remember organic compounds are compounds that contain carbon. So organic compounds, a lot of those bases contain a nitrogen atom. And the reason for that is the nitrogen atom will have that lone pair of electrons on it, and that can participate in this acid-base type chemistry. But what I really want to let you know about is these organic compounds that have a nitrogen in them, these are typically referred to as amines. And so we'll talk a little bit about of organic chemistry later in the semester towards the end. But these organic compounds that have a nitrogen in them are termed amine type compounds. So there's two types of weak bases. There's neutral substances. There are neutral substances, and as I said before, they usually have that nitrogen in them. And the reason for that is that non-bonding pair of electrons on the nitrogen, that lone pair of electrons on the nitrogen. And these amines, and here are 3 examples of them on the right-hand side: ammonia, NH3, methylamine, NH2, CH3, NH2, and hydroxylamine, NH2OH. So these are just three examples of amine type compounds. These tend to be weak bases. There's tons of these kind of compounds in the world. So the other is anions of weak acids. So that would be the conjugate bases. Remember we talked about acid and base strength. We had that chart and it had like the strong acids at the top and the weak acids in the middle and on down the line. Remember with each of those, there was a conjugate. And so with the weak acids, there was a conjugate base, which we defined as a weak base. So these are the two types of weak bases that you'll encounter: the nitrogen-containing compounds, known as amines, and then the anions to the weak acids, those conjugate bases that we discussed previously. Okay, here are some more examples of weak bases. We see methylamine here on the top. We see a few others. Actually, let me go back here. There's another table. We have ammonia, pyridine, hydroxylamine. All of those are those amine type compounds. You see the nitrogens are highlighted in blue along with their lone pair of electrons. And it's those lone pair of electrons that interact, and that those nitrogen atoms in those situations tend to pick up a proton, and then you have a positively charged nitrogen ion there. What we see on the right here, we see the Kb values. So we see ammonia, 10 to the minus fifth, pyridine, 10 to the minus 9, hydroxylamine, 10 to the minus 8. So what that tells us is that some of these are stronger than others. We see that pyridine and hydroxylamine, those are 10 to the minus 9, 10 to the minus 8. Those aren't real basic, so they're weaker ones. Ammonia is going to be a little stronger with that 10 to the minus fifth Kb value. Then this is the other part of the table. We have methylamine, 10 to the minus 4, fairly one of the stronger weak bases. And then we have some others as well that are, these fall into that category of being the conjugate base to a weak acid. So let's work through an example of how we would find pH for a basic solution. So this, as I said before, for a weak base, it's a similar approach as to what we did for the weak acid. So if you've been looking at the weak acid problems and you understand how to do those, you shouldn't have any problem with these. So let's go through one just to kind of make sure everyone's comfortable with how we approach them. So we're being asked to find the pH of a 0.15 molar ammonia solution. And so we go ahead, the first thing as we do with these, we write out our reaction. And that's equilibrium equation is NH3 plus water, give us ammonium ion, NH4 plus, and hydroxide ion, OH minus. We know it's an equilibrium expression because we've got the double arrows there. And that also tells us, because of the double arrows being equilibrium, that it's a weak acid as well. I mean, a weak base, excuse me. So then we write our equilibrium expression. So once again, it's products over reactants. So it's NH4 plus, that concentration, times OH minus concentration, and then divided by the NH3 concentration. We leave that water out because that's the pure liquid. That's a value of 1, so it doesn't show up in our expression. And so before we would have had a Ka value here, but because we're looking at a weak base, we're going to use the Kb value. And so that was given to us as 1.8 times 10 to the minus fifth. So we wrote out our reaction, we balanced it, then we used that information to write our equilibrium expression. We know it's a base because hydroxide ions are being produced in the products. So we then know we need to use Kb. And so we've set all that up in these first two steps. Step 3 hopefully looks familiar to you because once again, we're using our table of where in the top row, we have our reactants and then our products listed. And all of this is listed in molarity. That's the concentration that we use for these types of calculations, so moles per liter. And then the first row below that, we have initial concentration. We said we started at 0.15 in H3. And then so we get initial, so we have 0 of the other two. Then we have our change in the next row. Some amount X dissociates from the NH3 and goes to form that same amount of X of NH4 plus and OH minus. Then we go ahead and then express our equilibrium concentration. So that's 0.15 minus X, X and X for the ammonia, the ammonium ion, and hydroxide ion. So this general approach here is exactly the same as what we did with the weak acids. The only difference is we're using a Kb value instead of a Ka value, and we have a hydroxide ion concentration in there. We don't have a H plus ion concentration anywhere. Okay, so if we go ahead and fill in our things for our expression, we have that 1.8 times 10 to the minus fifth equals x squared over 0.15 minus x. Well, the nice thing about weak bases, it's similar to weak acids in that we can assume that that amount, in this case of the base that dissociates that we started with, we can assume that that number is pretty small compared to what we started with. So just, remember we did the same thing with the weak acids. We said we're going to neglect that. And the nice thing about that is now our expression becomes x squared over 0.15. And the beauty of that is by making that assumption, we don't have to do the quadratic equation. So it makes the calculation, instead of taking a page or two of writing numbers down, it's now just a little bit of space to go ahead and solve this for x. X is 1.6 times 10 to the minus 3. But let's just remind ourselves what x is. So if we go back to our table, we see that x is the hydroxide concentration, the OH minus concentration. We're being asked to find the pH, okay? So we got a little bit more work to do. If we were finding this for a weak acid, we have the hydrogen ion concentration and we just do minus the log of that and we'd be done. But because it's a weak base and we're trying to find pH, we have a little bit more to do. So we can go ahead, we have our molarity for the hydroxide ion. We can do minus the log of that. Remember, that's POH, that P is just a function. And we can do minus the log of that value, and we get the POH value of 2.8. One thing I just want to remind you, as you're doing these calculations, if you want to see if you're kind of in the right ballpark or if you hit an incorrect key or something on your calculator, if I'm taking a log of this, something that's 10 to the minus 3, this first digit in the value, after I do that, minus the log, it should be 2 or 3 or 4 or something around there. If it's 5 or 6 or something, I did something wrong, because that first number in the POH or pH value is reflective of the exponent for that 10 to the whatever. Then the next two digits, the ones past the decimal place, are reflective of what that number is that's multiplied by 10 to the whatever. So I'm looking at that, that's 2, it was minus 3 there, close enough, I'm probably doing okay. Well, remember we had a relationship that said pH plus POH equals 14, okay? That goes back to that water dissociation constant being 10 to the minus 14. And so P of the water, the KW, is 14. So we know that we can subtract our POH from 14, and that'll give us our pH, which is 11.2. So setting up the problem was pretty similar to what we've done for weak acids. To get it finally into pH, instead of hydroxide concentration or POH, we had to do a little bit more, but it's all based on relationships that we should be pretty comfortable with by now. Any questions on this problem? Okay. So there are a few homework problems I'd like to go over with you. Here's some that you can work on. I'm going to pull a few of these out and go through them with you just to make sure everyone is kind of on the same page on a few things. So let me go ahead and bring up the first one. The first one is 14.43. And so what we're being asked is to calculate the pH of each of the following strong acid solutions. Okay, so we've been talking about weak acids, we've been talking about weak bases, but remember we also talked about strong acids. And if something is a strong acid, what should that tell us immediately in terms of how we're going to handle the problem? Well, hopefully you're thinking strong acids dissociate fully. So remember, that was the difference between weak acids and strong acids. Weak acids dissociate a little bit, and the amount that they dissociate, that's where that Ka value came into play. Strong acids, they just go the same way. Strong acids, if you think about in the past, when we talk about strong electrolytes, those dissociate fully as well. So the beauty of that is, because it's a strong acid and dissociates fully, the concentration of whatever the acid is will equal the concentration of the hydrogen ion. So for the first one, we're told HBr is the acid and it's an 8.5 times 10 to the minus 3 molar solution. To find the pH of that, we simply do minus the log of that value, and that gives us a value of 2.07 as the pH. So pretty simple. So remember, strong acid, just like strong bases, okay, dissociate fully. We don't have to fool with that equilibrium stuff because there is no equilibrium. It just dissociates. In B, we're told we have 1.52 grams of HNO3, and that's in 575 mils of solution, and we want to find the pH of that. Well, remember when we're talking about things and we want to find a pH, we're taking the pH, we're doing that minus the log of a concentration, the hydrogen ion concentration. And that's going to be in moles per liter. So right now, we have units of grams for the HNO3, and we have units of milliliters for the solution. So what we need to do before we can calculate a pH is we've got to get a concentration that's in moles per liter. And so the first thing we would do is we would want to change this HNO3 into moles from grams. And so we're on the right-hand side here, I've calculated my molecular weight for HNO3. I add that up and get a value of 63. I can use that 63 value with my 1.52 grams of HNO3 to get my numerator into moles. Then the denominator, 575 mils of solution, to convert from mils to liters, that's a factor of 1,000, so I can simply slide my decimal place over 3 places to the left, and that 575 mils equals 0.57 liters. So now I've got my units where I have moles in the numerator, liters in the denominator. That's what I want for molarity. Excuse me. And I can do that calculation and get 0.0420 molar HNO3. Because it's a strong acid, the molarity of HNO3 will be equal to the molarity of the hydrogen ion. And so now I have 0.0420 molar hydrogen ion concentration. And then I can do minus the log of that to get a pH of 1.377. So once again, same ideas. Strong acids fully dissociate. The acid concentration equals the H plus concentration. We just got to make sure that it's in moles per liter before we do anything and try and find the pH. Okay, the next one, we're told we have 5 mils of 0.250 molar HClO4 and it's diluted to 50 mils. So once again, we've got some information here and we've got to get to where we're moles of HClO4 per liters of solution. So if we have 5 mils of that 0.250 molar solution, we know that the molarity is moles per liter. So we've got to get our mils into liters. And so once again, we use that 10 to the third, that 1,000-fold to convert. We know 1,000 mils equals 1 liter. And so we convert the mils into liters, and then we can multiply that times our 0.250 moles per liter value. And we get our our numerator into moles. Then for our denominator, it's 50 mils. We would do that same conversion to get the mils into liters. In this case, I chose to just slide the decimal over 3 places to the left to get 0.0500 liters. Go ahead and do that calculation. We get a value of 0.0250 molar HClO4. It's a strong acid, so that's the same concentration for the H plus. And then if we do minus the log of that, you get a value of 1.602 as the pH. So once again, a little bit of a variant from what we did before, but the same idea in terms of setting up and solving. So let's do the last one in this problem set here. We're told we have 10 mils of 0.1 molar HBr and 20 mils of 0.2 molar HCl. So we got 2 different strong acids here. Well, the beauty of this is they're all going to go to H plus, right? So it doesn't matter that one's HBr and one's HCl. So what we will do is we'll use this volume of each of them to calculate out how many moles of each of them are present. So kind of similar to what we did in part C of the problem. So for the first one, we convert our mils to liters, 10 times 10 to the minus 3 liters times the molarity to give us moles of that, HBRs. And then we do the same thing for the HCl, 20 mils there. We convert that to liters and then multiply it by the molarity to get moles of HCl for that. It's moles of HBr, moles of HCl, but really it's the same thing as moles of H in each place. So we can simply add those 2 values together, and that's what we see in our numerator here down at the bottom. We can add those 2 values together to tell us how many moles of H plus are in the solution. Then in the denominator, we need to figure out what our total volume is. In this case, 10 mils and 20 mils, so that's 30 mils total. And we want to convert that to liters. So numerator, total moles, denominator, total liters. We do that math, we get 0.167 molar. And then if we do minus the log of that, we get a value of 0.778 for our pH. So what you see here is in these examples, that is a little more straightforward if you're dealing with a strong acid because it fully dissociates. Whereas when we talk about the weak acids or weak bases for that matter, we have to worry about equilibrium and equilibrium constants and stuff like that. Any questions on the strong acid problem? Okay, so let's move on to a weak acid problem. So 16.55. So we have a vinegar solution that has a pH of 2.90. So as you probably remember from last semester's lab, acetic acid is what is the acid in vinegar. And we're told that its Ka is 1.8 times 10 to the minus 5. and we want to calculate the concentration of acetic acid in the vinegar. So previous set of problems that we looked at, strong acid, fully dissociated. Well, now we're back to weak acid, so we don't have that full dissociation. And so we're told that the solution has a pH of 2.9, and we're told what the Ka is. So for us, the first thing we're going to do, we're going to write our expression. Acetic acid dissociates into H plus and acetate ions. We write our equilibrium expression. So Ka equals concentration of H plus times concentration of acetate anion divided by acetic acid. We go back and look at our equation. It's all ones across in terms of the stoichiometry, so we don't have to do anything else with it. Well, now we're going to start thinking about filling out what's going on in the system. But we have this information of pH of 2.90. So what we can use that for is we can use that to calculate out what the hydrogen ion concentration is. So remember, if pH is 2.90, that's equal to minus the log of the hydrogen ion concentration. We move that negative sign over to the 2.9, so now minus 2.90 equals log of H plus. We take the antilog of each, so then that makes it 10 to the minus 2.9 equals the hydrogen ion concentration. So make sure you remember how to do that with your calculator, how to do 10 to the minus 2.9. You do that, and it tells us that the hydrogen ion concentration is 1.26 times 10 to the minus 3. I look at that and say, okay, pH was around 3. I got an exponent of 10 to the minus 3 there. That's about similar, so I probably didn't mess anything up. Well, the beauty of this now is, I go back to my reaction equation up top here. I know my hydrogen ion concentration now. I know from the stoichiometry, the acetate is going to be the same. So we know that concentration now, and then the acetic acid concentration is going to be whatever I started with minus that value. Well, what I started with on acetic acid is what I'm trying to figure out. So that's my variable, that's my x. So I go ahead and plug everything into my equilibrium expression. I get 1.26 times 10 to the minus 3 times 1.26 times 10 to the minus 3 divided by x minus 1.26 times 10 to the minus 3. So now all I need to do is solve for x. So I can do that. I can go ahead and start doing the algebra, and then it rearranges to this next expression, and then on down the line, and I can solve for x and get 0.089. So once again, as I said before in these kind of problems, part one is understanding how to set them up and getting comfortable with that. Part two is getting comfortable with that you know how to press the buttons on your calculator correctly to solve it. Because with these kind of things, and I think you saw that on the quiz, what we had a week or two ago, there's a lot of opportunities to hit the wrong button. So hopefully you understand it conceptually, but please take some time and work through some of these so that you get comfortable doing the calculations, because it does take a little bit of time to go through that. Okay, let's move on to 1673. So in this one, we're told that ephedrine, that's the stuff that's in a lot of decongestants, is a weak organic base, okay? And so then we're told that it's a 0.035 molar solution, and it has a pH of 11.33. And then we want to know equilibrium concentrations, and we want to calculate the Kb. So, okay. So what's some of the information we have? We have the concentration of it, 0.035 molar. We have the pH, 11.33. And we can write our reaction. It's the ephedrine plus water going to the protonated ephedrine and then hydroxide. So if we know the pH, we can solve that, we can convert that pH back to the hydrogen ion concentration, okay? We also, if we know the pH, we can remember that POH is 14 minus the pH. So if we subtract 11.33 from the 14, we can get the POH, then do minus the log. We know that means minus the log of the hydroxide concentration equals 2.67. And we have log of that, log of the hydroxide ion concentration, excuse me, is minus 2.67, and our hydroxide concentration is 2.14 times 10 to the minus 3. So we have 2.14 times 10 to the minus 3 hydroxide. We can go ahead in our equilibrium equation, subtract that from the 0.035, and we know that's how much is formed of hydroxide and the cation of the ephedrine, and we get these equilibrium values down here. So from there, we can plug those into our equilibrium expression, the products over reactants, and then we can solve for 1.39 times 10 to the minus 4. So now we know our pH, or we know our hydrogen ion concentration, we know pH, and we now know our Kb. So we also know these equilibrium ones as well for the 3 that are in our reaction. Okay, so those are some examples of doing some strong acid calculations and also some weak base ones. The weak base ones should be similar to what we did for weak acids in terms of approach. So now we're going to move on a little bit and talk about the relationship between Ka and Kb. So because when we talk about Ka and Kb, and we're talking about conjugate acid base pairs, and here's some examples up here of conjugate acid base pairs, and their related Ka and Kb values. And what you should see is that if you multiply Ka times Kb, it equals Kw. So that's for these conjugate acid base pairs. So if you go back to this table and multiply each of those by each other, you should get 10 to the minus 14, okay? The reason why that's important is, for these conjugate acid base pairs, is that what it tells us is, if we know either the Ka or the Kb value for it, we can solve for the other one. Because we know Kw, we know what water is, that's 10 to the minus 14. So if we know either Ka or Kb, we want to find the other one, we can do it through this relationship. Okay, so we're going to talk a little bit now, we're going to switch gears a little bit and talk about acid-base properties of salts. And so there's a term called hydrolysis. And hydrolysis is when something has a reaction with water and the result is either hydrogen ions forming or hydroxide ions forming. And so with salts, depending upon what the cation is and what the anion is, you can sometimes get protons generated or hydroxide ions generated based on how they interact with the water. So to determine if a salt is an acid or a base, you have to look at the cation and the anion in that salt separately. And so there's some rules around that, and we're going to go through some of those rules on how you kind of figure this out. So the cation, depending upon what it is, can be either acidic or neutral. So acidic just means it interacts with water, and as a result, you have some protons formed. Neutral means it interacts with water, and you don't get any protons or hydroxide ions formed. The anion, depending upon what it is, either you can have that interaction and the result can be some type of formation of protons, or it can have no interaction, be neutral, but it also can be basic. So depending upon the anion, any of those three things can happen. And as I said, there's some guidelines, some rules around these cations and anions to give you a feel for what's going to happen. And so let's go through some of that information. So anions associated with strong acids, those are neutral. So a classic example of a strong acid is hydrochloric acid, HCl. Strong acids, as we said earlier this morning, dissociate fully to where you have protons plus Cl minus. That Cl minus doesn't react with water, so no hydroxide ions are formed. So if it's, and this is true for all the strong acids. So the anions of strong acids are neutral. They don't do any reaction to generate with water to generate hydroxide ions. Now, if we look at weak acids, though, that's a different story. The weak acids, remember, if it's a weak acid, its anion is going to be the conjugate base. Weak acid, the anion of it, by definition, is the conjugate base. Since it's a base, and here we have an example reaction of acetate going to acetic acid. If it's a base, that acetate can interact with the water. We wind up with some acetic acid, and we also wind up with some hydroxide ion. So the anions of weak acids, since they are conjugate bases, they create hydroxide. So they have basic properties. Weak bases make sense. The third one, protonated anions of polyprotic acids can be acids or bases. Okay, remember, polyprotic acids, protonated anions of polyprotic acids. That would be something like, let's take phosphoric acid. It starts out H3PO4. You lose that first proton. You've got a negatively charged anion, but you still got protons on there that could be donated. That's what we're talking about in these cases. And it'd be the same for if it was a base. Or excuse me. And so this is what we're talking about with these polyprotic acids. Whether that next serves as an acid or a base depends on the Ka and the Kb of the ion. And so if Ka is bigger than Kb, the anion will be acidic. If Kb is bigger than Ka, the anion is basic. This gets a little confusing to figure out, to be honest with you, because you got to look at Kas and Kbs and compare them and all that. I wouldn't spend a lot of time worrying about that one. The first two, definitely you should know. The first two where you're saying that the anions of a strong acid are neutral, you should know that. And the second where anions of weak acids are conjugate bases, so they can produce some hydroxide, you should know that. The third one, I'd like you to know, but I wouldn't lose a lot of sleep over that one. Okay, cations. If it's a group 1 or group 2 metal, and remember, if you get your periodic table out, group 1 is stuff like lithium, sodium, potassium. Group 2 is stuff like calcium, magnesium, barium, stuff like that. So group 1 and group 2, those metal cations are neutral. So that means when they're in water, there's no protons generated, there's no hydroxide ions generated. Polyatomic cations are typically the conjugate acids of a weak base. So when we talk about these polyatomic, and by polyatomic, we just means that there's more than 2 atoms in it. And so in this case, we're taking ammonium ion, H4+. Those cations are typically conjugate acids of a weak base. And so the third thing is the transition and post-transition. So remember, the transition elements are ones where it kind of dips down in the periodic table. Post-transitions are the ones just a little more to the right of that. Those are acidic. Well, we're going to talk about that in a moment because there's no protons being exchanged, so why are those acidic? It gets down to how they interact with water. So the water that's attached to the metal, so if you think about it, you get some of this partial negative charge on the oxygen. That's what the red balls in the figure are for. In this case, the kind of orangish one in the middle, that's meant to be iron. So that has a partial positive, the oxygen has a partial negative. You get some association there, and you get this hydrated cation going on. The water that's attached to the metal is more acidic than the free water molecules, making the hydrated ions overall acidic. Now, how acidic really varies based on what the cation is. And we see that here with some of these acid association constant values. So we see here first, iron +3, the one we were just looking at, a pretty big Ka value, 10 to the -3. Chromium 10 to the -4, and then you see a big jump down here where we go to Fe +2, and that's 10 to the -10, zinc +2, 10 to the -10, nickel +2, 10 to the -11. So a couple things here. One is you can see it varies pretty widely based on which cation it is. The other is, just as a rule of thumb, cations with more positive charge, so these first 3 are +3 charges, those next 3 are +2 charges, you see quite a bit more acidity from the higher the plus charge. So 3, -3, -4, -5 for these +3s up here. These +2s, -10, -10, -11. You know, almost factor of 2x in terms of the exponents. So it really varies based on which particular metal cation you're talking about. So just to kind of sum up what we talked about in these last few slides. So salt solutions, are they acidic, basic, neutral? Well, we said you got to look at the cation and evaluate it. You got to look at the anion and evaluate it. For group 1 and 2 metal cations with an anion of a strong acid, that would be neutral. Because remember, we said anions of a strong acid, neutral. We said those 1 and 2 cations, neutral. So overall, it would be neutral. A group 1 or 2 metal cation with an anion of a weak acid, well, that 1 or 2 metal cation would still be neutral. But remember, what's the anion of a weak acid? It's a conjugate base. So that solution overall would be basic, driven by that anion. The third one we're looking at, we have the transition, post-transition metal cations or polyatomic cation with anion of a strong acid. Well, the anion of a strong acid, once again, that's going to be neutral, right? We said that. But we have said those transition, post-transition metal cations have some degree of acidity, right? Now, from our table that we saw, it varies based on what the cation is, but they all had some. And so that would be acidic. And then finally, the last one, transition, post-transition metal cation or polyatomic cation with anion of a weak acid. Well, this is where it gets complicated because transition metal cation or polyatomic cation, well, yeah, you probably get something there, right? But then we have the anion of a weak acid. So the first part, we can have some acidic nature. The second part, we can have some basic nature. Then it gets back to, we have to start looking at Kas and Kbs and see how it works out. So once again, like I said before on the other slide, this last one, number 4, it's great if you know it and you understand it, but I wouldn't lose any sleep over that. The first 3, you should be comfortable doing that type of designation overall. Because remember, first we talked about just anions, just cations. What we're doing here is we're kind of putting it together. And because remember, we have to evaluate both the cation and anion to figure this stuff out. Okay, when we talk about acid strength, if we have this generic hydrogen atom bonded to some other atom, and that's an acidic hydrogen, is that we have to have polarization there. So in other words, we have to have a little polarization. Remember, we wrote that, so we had that partial positive charge. In this case, it would be on the hydrogen atom, and partial negative on the generic atom, which we're calling A. So we've got to have that polarization. It can't be totally nonpolar. There has to be an uneven sharing of those electrons. The other thing is bond strength. But if it's a weaker bond, and that would mean you can break it easier, that means it's a stronger acid. Because you think about it, we need that proton to leave the molecule. That's what we're looking for. So if that bond between the proton and whatever it's bonded to, if it's a real strong bond, it won't leave, it'll just stay there. If you can force it to leave, then now you're acidifying your solution. The third thing that affects acid strength is stability of that anion, the associated anion. So if the anion that's left over after you deprotonate your molecule isn't very stable, then it's not going to be very likely to occur. These things like to be in situations where there's stability. And so if that anion is pretty stable, that means it's a stronger acid, because stronger acid means it's more likely to donate that proton and deprotonate. So for binary acids, and we define binary acids as hydrogen and then one other element. If we look at the periodic table, there's 2 trends that you should be familiar with. One is the acid strength increases as you go from top to bottom in a column, and then it increases as you go left to right in a row. So, and here in this table, there are some Ka values and Kb values that you can kind of take a look at. But in general, acid strength increases as you go from top to bottom in a row, in a column, excuse me, and increases as you go left to right in a row. So when we have acids that have hydrogen, oxygen, and another element, and that other element is a non-metal, those are called oxyacids. And in general, as the electronegativity of that non-metal increases, the acidity increases for acids with the same structure. And down at the bottom here, we see some examples of this, where we see COOH is more acidic than BROH and on down the line. And that goes back to the electronegativity of those values, of the non-metal portion that the OH is attached to. The other thing about oxyacids is that, and let's take a look at the structures here at the bottom, the hypochlorous, the chlorous, the chloric, and the perchloric acids. So what's the difference between these four acids? There's more oxygen. That's the only difference. They each contain hydrogen, oxygen, and chlorine. They each contain one hydrogen and one chlorine. The only difference is that the number of oxygens increased. So for this type of situation, there's two ways you can remember this. One is you can calculate the oxidation numbers and say as oxidation number increases, the acidity increases. Or you can simply note that as the number of oxygens increase, the acid becomes stronger. Personally, I remember it that way. When I look at these acids and I'm trying to figure out which one is the strongest, I simply look to see which one has the most oxygens. You can think of it either way, but like I said, for me, it's easier rather than calculating those oxidation number. It's easier just to remember more oxygens in a series like this. So we're just talking about a series like this. So it's these oxy acids that are pretty much the same. You're just tacking on another oxygen each time. The more oxygen atoms, the more acidic. Okay, another type of acid, and this goes back to the organic chemistry world. So there's an organic acid called the carboxylic acid. And a lot of times you see carboxyl groups written like this with, we see on the top here, COOH. What that's designating is that this proton, this last hydrogen atom, is easily deprotonates and is donated. If you look at the bottom of the slide, you get a little better picture of what's going on. So if we focus on the red portion, so the C double bonded to an O, single bonded to another O, in the carboxyl group, the one that has the negative on it, that would not have a negative, it would have a proton there, an H atom. And that's what you're designating with this COOH designation at the top. So carboxyl group has a C double bonded to an O and a C double bonded to an OH. That hydrogen on that OH easily deprotonates. Based on the pKa value of the different carboxylic acids, you get a feel for at what pH that deprotonates and which pH it stays on. And so one reason why this is so good is that at the bottom here, you see what they're calling the resonance structure. And what it tells us is that negative charge really in reality can be on either of these oxygens. And so that resonance structure, as we've heard before, resonance means stability. Stability means it works well. So it likes to be in this situation. So that's why it likes to donate that proton. And carboxyl groups are real common in the organic chemistry world. And we'll talk about that a little bit later in the semester when we touch on a little bit of organic chemistry. Okay, the last thing I want to just touch on is Lewis acid-base chemistry. So up until now, when we've talked about acids and bases, we've talked about protons being generated. We've talked about hydroxide ions being generated, things like that. It's all centered around H plus and OH minus. Well, there actually is another way to characterize molecules as acids or bases, and that's the Lewis acid-base chemistry. We're just going to touch on this very briefly. This is something, if you take organic chemistry, you'll get more than you want of this. This is big in organic. It's kind of outside the scope of this class, but I do want to just mention it so you are aware of it. So in Lewis acid-base chemistry, the Lewis acid is defined as electron pair acceptors, okay? The Lewis base is defined as electron pair donors. And we'll see an example in a moment of that, which will make it a little more clearly. So Bronsted-Lowry, remember that we talked about that definition. Those can be fit into the Lewis acid-base model, but compounds that do not meet but there are compounds that do not meet the Bronsted-Lowry definition that do meet the Lewis definition. And that's one reason why this kind of came about. As they were developing all this theory, they started realizing, gosh, we got stuff that's doing acid-base reactions, but there's no protons moving around and things like this. So here we have ammonia reacting with a proton, and that's in the top reaction. So that proton is attaching to the nitrogen, forming ammonia, or rather the ammonium ion, NH4+. And then on the bottom, though, we have NH3 reacting with BF3. And we see the nitrogen and boron reacting together. What you have there is, remember we talked about our definitions? Just take a look at that again. We said that a Lewis base is an electron pair of donors. So what you commonly see on this is you see the nitrogens, which typically have this lone pair of electrons on them. They can act as a Lewis base because they can donate those protons, or rather those electrons. And because they have that lone pair of electrons and they can donate, that makes them a Lewis base. In this case, the BF3 is a Lewis acid because they accept those electrons, and then you wind up with that reaction there. So a couple things I want to say about Lewis acid-base chemistry. Don't worry about the reactions, don't worry about that. Just simply remember, Lewis acids are electron pair acceptors, Lewis bases are electron pair donors. So it's just another way, in addition to the ways we've been defining acid bases that's out there. We want to make sure you're at least aware of it. We're not going to spend a bunch of time on it. You're certainly not going to be expected to do reaction mechanisms like this. Like I said, that's later if you continue on in chemistry. That's not for this class. That Lewis acid-base chemistry, going back, remember we talked about those metal cations and their interaction with water. That's where that explanation kind of comes out, is through this Lewis acid-base chemistry. I have one problem I want to kind of go through with you, and then we'll move on to the next chapter. So the problem I want to do is 16.75. So in this, we're told phenol has a Ka value of 1.3 times 10 to the minus 10. And so we want to write out reactions. We want to write the Kb for phenol. And for phenol's conjugate base. And we want to decide is phenol stronger or weaker acid than water. So here's phenol, C6H5OH. That gives us C6H5O minus, so we lose that proton. Phenols aren't hugely acidic, but they are somewhat acidic. And then you get the proton there. So that would be our reaction that we would write out. What I want you to remember is this relationship here in B. Ka times Kb equals Kw. So since we were given Ka, that's that 1.3 times 10 to the minus 10, and we know that Kw is 1 times 10 to the minus 14, we can plug those values into this formula and then solve for Kb and get a value of 7.7 times 10 to the minus 5. Well, is this a stronger acid than water? Well, the Ka is 1.3 times 10 to the minus 10. Kw is 10 to the minus 14. 10 to the minus 10 is more concentrated than 10 to the minus 14. So yes, it is. It's not a strong acid, but it is stronger than water. But all right, any questions on any of this stuff before I go on to the next chapter? Okay. Let me pull that next one up. Okay, so good news is more aqueous equilibrium. So you thought you were probably finished, but no, there's another chapter. But what this is going to do, though, is up until now, the equilibrium that we've been studying has been pretty straightforward. What you find is, as you go on with this, there's a little bit more nuance to it, and that's what some of the stuff we're going to look into. And so a lot of this centers around buffers and impact of ions and things like that. So the first thing we're going to talk about is something called the common ion effect. And so if you think about a weak acid or a weak base, is you have partial dissociation of it. And if it's a weak acid, for instance, you always have that anion floating around in there. Well, if you think now, if you have electrolytes in there, strong electrolytes, or even a weak electrolyte, then you could have some common ions there. And if we think of this based on an equilibrium situation, if we start introducing things in, we've learned before, if you introduce things, it drives the equilibrium one way or the other. And that's what happens in the common ion effect. And so that by adding ions that are already there, so for instance, we'll look at an example in a moment of acetic acid and sodium acetate. You push the equilibrium one way or the other. Now, what I want to point out is that the equilibrium constant doesn't change. The equilibrium constant, by definition, is a constant, and so it is what it is. That just means all the other stuff in there has to change their concentrations to get that products over reactants value to still equal whatever the K value is. The other thing we'll see a little bit later is that this kind of stuff also affects solubility, and sometimes you can impact solubility, you can precipitate stuff out, things like that, by adding some of these ions in. So, but first, let's take a look at this acetic acid example. So, as we know, acetic acid is a weak acid. So we have acetic acid in equilibrium with hydrogen ions and acetate ions. If we take sodium acetate's a strong electrolyte. Since it's a strong electrolyte, that means it dissociates fully. And notice when we drew this equation, it's a single arrow. That tells us even more so that you put that in a solution, there's no NaCH3COOO in there. It's all either sodium ions or acetate ions. So now in our solution, if we have an acetic acid solution, we have this first reaction that took place, but then now we've got a bunch of acetate in there. That's going to mess up things because we've got to have that products over reactants value still equal to whatever the constant is. So what it would do is it would shift things over to the left, and that hydrogen ion concentration would go down to try and balance things out. Now, exactly what the final numbers for all this stuff would be, we have to sit down and do some calculations. And lucky for you, we're going to get to do that in a little bit. Okay, so let's take a look at one of these based on that acetic acid and sodium acetate example that we just talked about. So we want to find the pH of the solution that's formed by adding 0.3 moles of acetic acid. So that's the CH3COOH, and 0.3 moles of sodium acetate. Okay, and remember, sodium acetate we said is a strong electrolyte, so that's going to fully dissociate into acetate ion, and we're doing it in 1 liter. So here in step 1, we have our reaction, our equilibrium equation. In 2, we have equilibrium expression. Once again, products. H plus times acetate concentration divided by reactants. The acetic acid equal to our acid dissociation constant. So we've been doing that for a while now, writing out the chemical reaction, then the equilibrium expression. Now we go and we set up a table. So initially, we're told 0.3 molar acetic acid. Initially, we're told 0.3 molar acetate, sodium acetate that we added in. And then from this dissociation of the acetic acid, we would have minus X there, plus X, and plus X. So we sum all this up, and we get an equilibrium. We'll have 0.3 minus X, we'll have X, and then we'll have 0.3 plus X. We go ahead and then put our values in. We have X times 0.30X, 0.30 plus X in the numerator, 0.30 minus X in the denominator. We're going to do our assumption that we've been doing with weak acids and weak bases. We're going to do that again here and say that the amount of X relative to 0.3 for both the products and the reactants is pretty little. So we're going to ignore that. This goes back to what we've been doing with the weak acids and weak bases. That allows us to rewrite to 1.8 times 10 to the minus fifth equals X times 0.3 divided by 0.3. That's pretty easy math. Those 0.3s cancel. And X is 1.8 times 10 to the minus 5 as our hydrogen ion concentration. We want pH, so we do minus the log of that, and we get pH of 4.74. So the idea there is we did a pretty similar approach as we've done all along in terms of writing out our equation, see what the coefficients are, then using that information to write the equilibrium expression. Then once we did that, then we went and set up our table. Table was a little different because a lot of times we just had one initial concentration value. This time we had two, but then we had a change in concentration of that acetic acid that we started with. That's similar, minus X plus X on the product side. And then we added those things up to get our final equilibrium concentration values. And that's where we had the 0.3 minus X. We have X for the hydrogen ion concentration, and then 0.3 plus X for the acetate ion. Similar to what we've been doing with weak acids and weak bases, we say that that change value relative to some of these bigger concentrations isn't significant. We're not saying nothing happens. I want to stress that. We're not saying nothing happens. We're just saying it's not significant. So for the purpose of our calculation, we're going to ignore those two plus X and minus X values, make the math a little easier, and then be able to get our pH that way. Okay, so what we just said about weak acids and common ion effect and how it impacts things, it's the exact same for weak bases, okay? So if we add something, so in this example here, we have ammonia going to ammonium ion and water. It's the exact same, and hydroxide is the exact same thing. If we added some ammonium ion, NH4 plus, it would shift that equilibrium back over towards the other way, and it would lower our hydroxide concentration. So the acid-base thing, really the concepts are the same. It's just some of the details about H plus or OH minus that's in the reaction that you write. So all this leads us to something that I know you guys have worked with in lab, and you hear people talk about just in general. People always talk about buffers, right? Buffer is a pretty generic term. It's not just a chemistry term. And so in chemistry, though, buffers are based on conjugate acid-base pairs. So these weak acid-base, conjugate acid-base pairs are what we define as buffers. And buffers are simply something that you can add some acid or add some base to, and it doesn't fundamentally change the pH of the solution, okay? We're not saying it doesn't change it at all. If you really measure it really precisely, you can see some differences, but in general, it's pretty much the same pH. Now, there are some rules around buffers, and one of them is you need the acid form and the anion form to be fairly concentrated and to be similar concentrations. And by fairly concentrated, we're talking about 10 to the minus third molar or higher, okay? So you've got to have some concentration there in terms of the buffer. And the other thing is you can't have a big mismatch on the concentrations. They need to be pretty much the same. They don't have to be exactly the same, but they got to be in the same ballpark. There's two ways you can make a buffer. One is to take a weak acid and add the salt of its conjugate base. So that was the example with the acetic acid and the sodium acetate. So that would be an example of someone preparing a buffer where they took acetic acid, and I think it was 0.3 molar, and they added 0.3 molar of the acetate. The other way is to partially neutralize a weak base by adding a strong acid, or vice versa. So in other words, you can take something, you can take a weak acid or base and then partially neutralize it with a strong of the opposite. And so either one of those ways are ways to, in the laboratory, make a base. Number two is easier to do. Number one takes a little bit more work, but they both work and they're both done. Okay, so how does buffer work? So in this case, we have our HF and F minus here in the middle of the diagram, and we're saying that those concentrations are equal. You add a little bit of base, it will react with some of the acid to form a little bit more of the F minus, but the pH really doesn't change. You add a little bit of acid, H plus, that'll lower the concentration a little bit of the F minus, but you don't get a huge difference. The pH stays pretty much the same. You have a little bit of change in HF concentration. So at the bottom, as it says here, you're neutralizing a little bit of one of these, depending upon if it's acid or base. So the pH doesn't change much. That's the key phrase there. It's not, like I said, it's not saying there is no pH change. It's just usually pretty small to the point of where people don't worry about it. And that's the idea behind the buffer. Okay, I want to go through just, when we talk about calculating the pH of a buffer, there's a special way you do that. And so if we think about a weak acid, which is what we're usually talking about with buffers, we have our equilibrium expression here. So Ka equals H plus times the anion concentration divided by the acid. If we go and take minus the log of both sides of this equation, we then get minus the log of Ka. We break out that H plus concentration. We have minus the log of that, plus minus the log of the ratio of A minus to HA. If we rearrange that, and by rearrange, what we're saying we're doing is we're taking this plus this minus log A minus over HA and taking it over to the side with the minus log Ka. If we do that, then this minus log A minus over HA becomes plus log A minus over HA. So then we have minus the log of the hydrogen ion concentration equals minus the log of Ka plus log of A minus over HA. Hopefully, when you see minus the log of something that looks familiar, and you realize that's the P function. So what this really is saying is pH equals pKa plus log A minus over HA. And sure enough, that's what we have. And that expression is known as the Henderson-Hasselbalch equation. This only applies to buffers, okay? But this Henderson-Hasselbalch equation is what you use to calculate pHs of buffers. Because you're going to know the pKa of your acid, or you're going to know the Ka, and then you can calculate the pKa. You're going to have information about these concentrations, and then that allows you for buffers, remember, to use this Henderson-Hasselbalch equation to do the calculation. Okay. Here's an example of this. We have lactic acid, 0.12 molar. We have 0.1 molar lactate. We have the Ka for lactic acid. We would go ahead and fill in the values for the Henderson-Hasselbalch equation. So we know the A minus concentration, that's 0.1. We know the HA concentration, that's 0.12. So we can do the log of that ratio. pKa, we know that P function means minus the log of the Ka. So we have minus the log of the Ka value, which is 1.4 times 10 to the minus 4. We go ahead and do those calculations, and we get a value of 3.77. So remember, Henderson-Hasselbalch, that's the equation we used if we want to calculate the pH of a buffer solution. All right, we're going to end there for today. Just to repeat what I said at the beginning of class, Tuesday, we will finish up chapter 17, and then a week from today, next Thursday, we will have our third exam, which will cover 15, 16, and 17. All right, thank you.